Hello and welcome to I Like to Think with your host, Player One. Yes, that is what I'm going to be identifying my name as for now. But, anyways, this is just going to be me trying to think, to rant, to think about things that are sciencey in nature to be corrected in the comments. If there are any comments. Now, I already tried doing this, so I already have a thought going through my head. Wires. We know them, right? We know that they go from path of least resistance to its path, or sorry, it goes along the path of least resistance. Now, my question is, does it really? Does it go from the path of least resistance or the least resistant path? Now, this may seem like gibberish to most, but there is two very different terms for this. Because this right here, this is going to be representing a copper wire. Just straight up copper. This is going to be representing just a wire. A wire that is slightly more resistant to the flow, less efficient at conducting energy than copper, thus making it a more resistant path. But it's shorter than the copper path, and this mystery material is going to be just close enough to copper's conductivity that this path right here is less resistant in total than this path, which means that this would be a experiment to see what makes what go where. This right here, the copper. If it travels along this path, then we shall know that it goes along the path. It goes along the path of least resistance. It goes along the least resistant path instead of the path of least resistance. Or in other words, we're asking the question total or over what's its face? Total over in the I don't know how to spell that crap. Total over individual. Now we can figure out which one by simply putting down LEDs. And if you're wondering why would this matter, the answer is that you can use it to make different things function. But simply put, you would have a LED here and LED here. If this one lights up, it goes along this path. If this one lights up, it goes along this path. Now, the reason why this would be important to know is because you can use this to actually make things. Because this is a little idea. I forgot what they're called, but they just make sure that you don't overdraw electricity or something so you don't burn out circuits. I can't quite remember. Breaker, I think. Anyways, so instead of having a wire burnout, which is how I believe that they work, though it might be a little bit old school, instead of having a wire burnout, you just have two paths. This is considering the total over the individual. You have this positive, this little segment highly negative, and this segment negative. Now, when the current goes over here, it doesn't jump, or at least it might, depending on how we would go about it, because there are two possibilities. One, it looks at it at a whole, and two, the reason why electrons is because of gaps and gaps and excess. The gaps pull, the excess pushes. So this would be in forces like this. And this one would be in forces like this. When you create electricity, you create both a gap and a excess. Now, if you notice anything, there are two lines corresponding with this. But what this would basically mean is that this one and this one agree, and thus that is how it shall travel. That's where the extra electron will go. Now, why this is important is because if that is the reason why paths are chosen, that means that if this is highly negative, and this is also negative, but then this all of a sudden goes up and up and up, my question is, at what point do the electrons want to jump from here to here? Now, the question has to mostly rely on atomic theory, I believe it is. Protons and neutrons. Let's use red for protons. This right here will simulate the charge of the atom. Highly positive. Now this charge wants to draw in electrons. Now this is just assumption because I am smart, but I'm uneducated, so kind of contradicts itself right there. So this will pull in any electrons. Oh, that's not showing on the screen, is it? Well, just know that this is going to draw in any electrons. And the amount of electrons determines on how much it shall pull. So this right here, these are the electrons. These electrons are going to push against other electrons. So if you have too many electrons, one's going to get flung out. Hence the excess in void. When you don't have enough electrons to counteract the forces in here, then the electrons, hold on, let me just quickly, then the electrons are going to, if you have enough for this to counteract the pull, then the electrons are going to leave. If you don't, then the electrons are going to come. So, how many gaps inside of this little segment here do we need before it pulls hard enough to rip the electrons from this path to this path? Or in other words, how much of a force do we need to make it go from here to here? So, when there is a gap, there is a pull force. When there is an excess, there is a push. So, if we have a lot of electrons here, and a lot less here, when this will reach a certain point where the electrons really, really, really want to leave, they will go from here to here. But otherwise, they will go around this path, the path where they don't have to go between empty air. Now, that is all just complete theory and thought. But this would also be a good experiment for that, figuring out how would it need to go. But how this would function as a breaker is basically when this has a surge of electrons, this would be flipped, wouldn't it? Well, I'm just going to use the plus as presence of electrons and minus voids. Voids, presence, voids pull, presence push. Now when this is pushing, this is pulling. But also, this right here is also pulling. So thus, this pushes and gets pulled over here to a sort of section, I would believe. Like little slots being filled up. Say each one of these is a slot in a Tetris place. Or Connect 4. When you have something here, it wants to go down. And so it will. And it will fill in that space. Now say this one right here was blocking one above it. Now it's first. Let's say this one was blocking one above it. And so, as this was here, it stopped it. Sorry, as this was here, it stopped this one from going on. Now, when this one moves, this one will too. But we are not dealing with Connect 4 here, and I realize my flaw. And I see we're dealing with actually something closer to air. Air that can be imagined as a bunch of little particles. A lot of really small particles. Now these small particles move randomly. At least we assume they do. And when they, at least I assume they do. When they move randomly, they go in any direction. If there is a particle for it to bounce off of, it will go in the opposite direction, most likely. And thus, if there is no particle in an area, things are more likely to travel there. Because when it moves about, the places that don't have any space, or anything in that space, will be more inviting. They won't repel, they won't push, there won't be anything to block it from going in there, and thus it will. It's like throwing a bouncy ball at a brick wall. When you throw the bouncy ball at the wall, the bouncy ball comes back. The bouncy ball is our little atom of air, and when it comes back, if there is another wall right about here, the bouncy ball will bounce off that. Now we'll keep on doing this, and it will always do this, but you will never, you will see the ball at this place for only a certain amount of times. Those times are when it bounces off, and thus, for the short time it's here, it's going to leave in the same moment. And thus, the place where you're most likely to find the bouncy ball is in between the two walls. That's what's going on here. Everything keeps on bouncing back and forth, back and forth, and back and forth, and back and forth, until it finds a space where it is. Because in reality, this has to do with quantum states. If you know what I'm talking about, then nerd. Nah, I'm joking. But quantum states are basically, from my knowledge, not knowing what's in there. Like Schrodinger's cat or box. I don't know if we define it by the box or the cat, but that's besides the point. Basically, there's a cat inside this box. Now this cat is in there with a little vat of poison. And don't question the cat. The cat is as the cat will be. Now this vial is filled with poison. If the cat spills the poison, the cat dies. Now, we have closed the box. The box is sealed. We can't see into the box. So thus, that is absolutely horrendous. So thus, the cat is unknown at if it's alive or dead until you hear a shatter, but we don't actually. Let's just imagine that we can't hear anything inside the box anyways. Now, when you open up the box, you'll know if the cat is alive or dead. Now, it could only be one of these two things. And as time goes on, it's more likely for the cat to have spilled the poison. So thus, it probably will. So our little fella. So basically, how this relates to air is that the air is anywhere within a sense of probability. This probability is predictable. It is a curve. That's a sucky probability curve right there. Let me see if I can do this. It's better. And that's even better. Basically, this is the most probable, and this is least. The closer you go in, the more likely something is to happen. It's an exponential curve on both ends, curved out over here. Now, this is where you're going to find the error, most likely, because every moment is a time where the probability is rolled. Every second, every time you blink, every time you breathe, every moment, every frame of the mind, every time that you can perceive, it will be somewhere else. Now, this probability is less of a where it is and more of a what direction is it heading from the last place you viewed it. But if you never viewed the air, this would be where it is. Now, I can't remember how we got here, but we did. Now, quantum, blah, 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 blah. Now, something that you may not know is that technically, we ourselves are constantly inside of a quantum state. Now, why this is a little strange. You know where you are, you know what you see, and you have great understanding of where you're heading. But, to somebody else, say our little cat inside the box, he can't see you, he can't hear you, he can't smell you, he can't do anything, he can't perceive you. And most importantly, he can't taste you, thankfully. Now, this cat doesn't know where you are. Though, if the cat ever saw you, it would know where you last were at that moment. And thus, where you were, or where you are, is completely unknowable to the cat, as long as he cannot perceive you. And as long as he can't perceive you, you are in a quantum state. But as soon as he does, he knows exactly where you are. But until then, you could be anywhere that the cat cannot see. And since the cat is within a box, everything else around it, the world itself, is inside of a quantum state. Now, when you're stuck inside of your room, or more like it, you are willingly trapped yourself in your room. You have shut yourself off from the outside world. This is your box. Now, there are people all around you every day. There are people outside and far away in distant countries. Let's draw... I can't remember what it is, but it looks like a boot. Is it France? Is that France? Oh no. Let's draw Chile. That's close enough. But anyways, there are people here too. That's the entire point of this. And to all of these people, they know not where you are specifically. They know you're here. Actually, this guy knows you're here. This guy knows that you're somewhere around in... what's his face? In the United States. If you are. And even then, you might not be known for that, because something that you can know is that I am here. But you know not where. You just know this general term. This is, in most terms, for everyone out here, you could be anywhere but here. But anyways, basically there's this big probability curve of where you can be. This place is where you are, most likely. And this place is where you're least likely to be. So, in other words, this probability curve has layers. It's like an onion, it's like ogres. Someone who knows a general sense of where you are will have a different probability curve for someone over in Chile. Unless if you live in Chile. Then, when you live in Chile, they will probably have a better idea. But, for everyone close to you, they will have a probability curve of where you are in your room. Probability curve, actually, just a probability, lots of probabilities, where you are. They may know you better. And when they know you better, they can guess where you are better. They can guess if you're in your bed, if you're on the floor, or if you're at a desk doing work. Let's see, old-fashioned computer. I'm not drawing it with a pen. That's good enough. Anyways, so they have a couple of options where you might be, and there's plenty of them. But they know that you're most probably in your bed right now or at your desk. Very little of you are probably going to be on your floor. And so thus, your probability is probably something like bed, desk, floor. Something closer to that than this. But simply put, you are currently inside a quantum state. You are to be guessed. And this actually has to do with something that's very big in our day-to-day lives nowadays. Something that has been making ramp prices ridiculous. We all know it, and we all have our opinions on it. AI. Now, AI works similar to a probability curve. It's a guess. Now, what this means is simple. It works off of, at least from what I know, it works off of a chain of probabilities that I know of from, it has to do something with nuclear physics. But anyways, this has a chance to go here and here at the same time. So let's probably make that one little arrow. Now this, let's say this is a 50% chance. Now there's a chance for it to repeat into itself, which is, let's say, 25. And there's a chance for it to end. Let's make a little circle here. And let's say that's 25% chance. Now when it goes over here, it goes into both of these, which is just this, a unit. We're calling it a unit because it's, nothing in particular. Now, this same thing happens to it a lot. If you start with 1, there's a coin flip on if it's going to survive. If it does, you now have 2, which is now a better shot at 1 happening. Or simply put, you go from 1 to 2 to 4. First one, you have a 50% chance of success. Second one, I believe it's closer to 75. But let's say, just for fun, that it's 100. Because I don't want to do math. Now over here, you have 200%. Now this isn't actually a success chance. This is a double chance, or since I don't want to have to do English here, times 2 chance. At 50%, you get this, but you can also get nothing. You can get nothing, which is if you fail the coin flip. Now from here, you can actually go back into 2%, 2 of these fellas. But you can also go up the ladder. Now the shot of it going up the ladder means you have to roll 50% twice. Now, what happens is basically it goes from 100% doubling chance, 100% success rate, to, let's see, 25% chance success rate, which means I'm just gonna have to move you to a 75% chance success rate. So this one would be 50, and this one would be 25, with a near perfect chance of it going back into itself. And since this one's 25, let's say this one's 75. Now, this isn't actually true, because there's also a chance that it dies, which means that it's probably closer to not 75, but 75 split, which would be, okay, so we have 75, let's remove the 50, that's 25, so that's 2.5% chance that does this, and a 12.5% chance that does this. Now, on that 25% chance, it goes up here. But on that 2.5, it happens again, which means in reality that we are dealing with a 2/3 probability here and a 1/3 death. Now, when you get up to here, on that small chance, you now have 4 units to deal with, each one having its own probabilities, which means that if only one succeeds, you go back here. So let's go back to here. Let's say 4 has a chance of 2, 0. We know it has a chance of 8. It also has a chance of 4, and has a chance at 6. Now let's see if we can try and decipher each of these probabilities. So each has a 50% chance of success, at least each one of the individuals in the 4. Which means that in order to find the chance that it doubles, we would have to figure out what happens. We would have to take 50% and put it to the power of 4 to see what our chances are there. Now, I'm just going to quickly whip out a calculator. Or not. Okay, so let's just do division, since this is always 1/2. That means we go from 5 to 2.5 to 0.25. 1.25 goes into 0.6, 0.6, 0.64, I think, because when you do this, because that's perfectly 1, so that's 5, so that's 2.5. Okay, and since this is 50%, that means that we just move it over to the right, so that means we have a 6.25% chance of this happening. Now for 4, we need 3 to work, but it doesn't need to be in a row, which means 3 out of 4. What's the chance that... Okay, this is some serious math. This is serious math for me. So let's say one would always have to fail, but each one has 50% chance of success. Well, let's put that to the side for now. Okay, 50, 50, 50, 50. Okay, so then that would be 25, I believe, actually. No, because you'd be going against all of these guys. The 3. If the 3 works and the 1, so that means this is a lot more work than I thought it was going to be. Let's just say 4 is a 50% chance, because it is half of these. So if we're going by the same logic, then 6 would be 25, I believe. Let's just go with 25. 2 would be, let's say, 12.5. And then 0, let's say 6.25 as well. So This would be that, which would make another 25%, which means that this would all work. Or, in other words, it gets really complicated real fast. Because, in truth, AI is an aneurysm. Because AI isn't AI. AI is a probability model, a dependency probability model, as I'd like to say. So that's what I've named it inside of my head. You calculate off of your starting position. What are the chances that A, B, C, and D happen? Now, we don't actually have to calculate all these things because, it's going to be boring. But simply, anything that predicts anything, any probability, would thus be able to be called AI if it works on anything that is dependent. Anything that works on a dependency or in. The next step relies on the last step. Now, considering all this, AI would seem less real, because it is, in fact, a simulation of what is real. But a simulation can sometimes be the real thing. What I mean here is that the real question isn't if AI is you, but if you are AI. Now, the question here is about the brain. Does the brain work off of these same probabilities? The 1 goes to 2, goes to 4. That can go anywhere from 6, 1, 2, 3, 4, 5, 6, to 8. 2, 3, 4, 6, 7, 8. All with different layers. You can't go from 1 to 8, but you can go from 1 to 2 to 4 to 8. But you can also go from 1 to 2 to 4 to 6 to 8. But then from there you can also go to 12. So you can go from 1 to 2 to 4 to 6 to 8 to just about anything counted in even numbers, which would mean 10 and 12. And this is when we stop at 6. You'd have to stop at 16 for 8. But simply put, 1 you can't skip, at 2 you can't skip, at 4 you can skip, at 6 you can skip, with each one becoming more and more big of a gap. Now, my question is if the brain does this. If it does, then that would mean that we made artificial intelligence. AI. If it doesn't, then we have not yet made AI. Now, this in itself might, in fact, be a probability model. One with, I would say, a 90-10 split. That is, until we reveal it. So, in short, this is in a quantum state. A state of unknowing, a state where two things are possible at once, but only one can be. And depending on what the answer is, you will never know. And so this is how we go from wires and their possible flows to me rambling on about AI, the brain, and dependency probability models, which I would like to say are applying the rule of big numbers rule of egg bears. 2 dependent cases. Also, if you're thinking you can get a perfect bracket from this, you can, but the fear is that the probability of a perfect bracket looks like this. I don't know what that is. But this. If this is what the perfect bracket looks like, then this would be the maximum area. Or, how do I escape? Get back into you. This would be the area of probability using a dependency model. And you'd have to try and cover as much ground here as possible. So, in the end, if the model looks like the model for a perfect bracket is this, it won't matter. But if it's this, you can use it. So anyways, apparently got March Madness in here too. I did say it would be random. But that's all for today, folks. Ta-da! The inside workings of a madman, given to you by Player One. Nah, I'm joking. I'm not mad. Not yet, at least. And until next time, see you.